Okay, so same system now with different type of setup. We're looking at this type of coil here. So on this one we looked at the last time, we have 3 pins which are direct contact. Center one is connected to primary winding in this one. The outside one is the other side of the primary winding, and the outside one is the opposite side of the primary winding in here. So no module here now, because the module has been taken now and is incorporated as part of the engine ECU. So when we're probing this one, we will be probing into one of these pins here. Now if we probe into the center pin, I'm going to get a solid line of 12 volt feed in. So to see if the signal from each one, I can probe into pin 1 or pin 3 here, which is the opposite end of the primary winding, and I'll pick up what's happening here. Now remember, we've seen in one of the videos earth switching. So this is the positive side of this particular winding, this is the earth side. So we're on the earth side of the winding here. So we will see a voltage when we probe onto it. And then when the circuit earths it here, we will be on the earth side here, so we will drop down from our original reading. So it's just a different type of setup, but what I want to see is the primary winding working? So remember, primary winding, we said, if we leave aside the secondary stuff for a minute, with a 12 volt feed in, builds up, saturates up the magnetic field, there's a laminated iron core in the middle here, magnifies, the function of that is to magnify up the magnetic field to give it its full strength, and then suddenly we cut the primary winding, make it go open circuit. So it self-induces, but because it's a sudden close to it, there will be like a backlash of a wave. So we will self-induce into the primary winding a voltage in excess of 12 volts, the speed we're given, right? So it's like water flowing along a pipe, and then suddenly you'll slap the door closed on it. The back wave that comes over, it spikes up higher than the actual flow through. And that's what we're going to see here on the primary winding. Now we've seen this before on the Kettering system, this backlash up, this spike in the voltage that we're going to see on the primary winding. And we know, right, it's going to get up 2, 3, even 400 volts, depending on what is happening inside that primary winding. The spike we see is going to be that high. So our meter setup is going to be slightly different. If we take a look at that meter, again, it's a single channel we're looking for here. So the scope set up on it. If I go in here, I'm going to set the voltage somewhere up around here, right? Now, under normal circumstances, when I'm connecting the lead to my scope box, I go directly with the lead to it onto the channel here, channel A for us. But because I know it's going to be quite a high voltage spike on it, and I don't want to damage this machine, if you zoom in on that there, we'll see this is an attenuator, and it's a 10-to-1 attenuator, right? So it's going to allow us to see that high voltage without there being any risk to damaging the actual machine itself. So I put it on here. I have to tell the scope that it's on. So when I go in here, we see our probes here. Now normally it's just a standard by one signal we're looking for. But because this is quite a high voltage we're going to be looking at, if we come down here into the automotive section, and we'll see there's 2 listings here. So a 10-to-1 or a 20-to-1 attenuator is what we're going to look at here. We're picking 10-to-1 and we're done. It will automatically bring up this here as a high voltage on it. So anywhere between 100 volts and 400 volts is what it's going to cater for. Again, our time scale really, really low here. You can start at 20 milliseconds per division because this stuff is happening so fast. We've actually put it up to 50 milliseconds here so we can take a look and see what's going on, and then we're ready to go. We can see the automatic setup here. We run all the way from 0 volts down here all the way back up. It'll go up and read up as far as 400 volts here on it. Our time scale again then is 50-second divisions, so 50, 100, 150, and on it goes all the way up there. So we're ready to see our primary waveform. And remember, that's what we're going to see now. We're not going to see a signal on and off. What we're going to see is an actual primary waveform. So there is our coil in here, like we've seen out and tested out on the bench. 3-wire section to it. So the middle wire, we said, is a positive feed, and then we have the opposite side of the primary winding, and this is going to connect through our engine ECU here. So control for this coil is inside this engine ECU. Still through a transistor, but it's inside here as opposed to an ignition module actually sitting on top of the coil itself. So again, we break out wires here on it. If it was a car that came into the garage, again, you'd have to back probe, but make sure if you're back probing that you are very, very careful sliding the pin down the inside of the moisture plug so you don't damage it. If we go directly into one of them, and I think this is coil A here, and just probe it there, we'll see what waveform is displayed. Now, we can see loads of what's going on here. So every time coil A sparks, we're seeing something here, right? So if we want to stop it here, and again, we want to really zoom in here on what's going on. So come up here, select your zoom button, take it from the top of this wave up here and back slightly, and we want to zoom in on this section here. Now, what we can see here is a perfect primary waveform. So, remember, when the earth is broken to the primary waveform, it's at 0 volts, right? But because we're probed on the earth side of it, we're actually probed on one of the 2 outer ones, pin 1 or pin 3. When there is no circuit there, we're on the feed voltage. When the ECU earths that circuit, we are now probed on the earth side of it. So we will see a voltage dropping down here. Because we're on the earth side, there's our voltage drop coming down here. This allows current to flow through the primary. So this part down here, where we're seeing 0 voltage down here, will be the dwell time. How long current is flowing through the primary circuit. And then suddenly, the ECU breaks the earth for the primary circuit, so we get this surge of voltage spiking back up here. And like with anything that I take up to a height, when I drop it, it's going to bounce to settle back down onto our battery voltage again. Because remember, now we're back connected to the positive side of it. So, if we use our lines again, we pull this side in here, and we say, right, current starts to flow through the primary winding at that point there. Our next line along here, right on this line here, is where current stops flowing through the primary circuit. So if we look up for our delta here, our difference between those 2 lines, current is flowing through that primary winding for 3.91 milliseconds. So there's our dwell time there for that particular event on it. Now remember, these events are going to vary for every single spark event that we see along here, ever so slightly. If we pull that box out of there for a minute, because we want to see how high did this voltage spike up from. So, let's see. We bring it down. Here's our feed voltage here. Remember, here's our feed voltage along here. And here's where the spike went up to. Right to the top of that peak there, which is right up here. So there's our supply voltage, our 12 or 14 volts when the engine is running down here. There's our top one up here. And if we look to the box over here, we get a voltage spike here on the bottom of 391.8 volts. So there's our spike in voltage when we suddenly switch off the primary winding. So that's what's self-induced into the primary winding, 391 volts. Now remember, at the exact same time, we mutually induce into the secondary of approximately 100 times more. So if we went 100 times more than that, we now have 39,000 volts pulsing out of our secondary winding, going down to our spark plug. The other thing we can see on this, and we'll just close that out there for a second, get rid of all those lines, is here. Where the voltage peaks, and then we see another peak here. This is actually the spark duration, or how long the spark or arc across the spark plug actually lasts for. So if we pull our two lines across again, so that's where we stopped it, that's our voltage peak. This section here is going to be our spark duration. And we can see up here, our spark duration lasts for 1.3 milliseconds. And then when we look back here on it, we see, we oscillate out here. It's like taking a football up the top of a house and dropping it. When we drop it, there's the length of time it takes for it to drop over, and then it bounces until we oscillate back out and we end up back at our battery running voltage or engine running voltage, 14 volts or so. This oscillation here is normally a good sign that the coil is good. So anywhere between kind of 2 and maybe 5 oscillations are showing me the coil is actually in good condition. If I suddenly bounce and stop, it's like having a flat ball. So something is going to go, while it's still a ball, something is going to go wrong with it. It's not oscillating out properly. So it's an indication that that coil may be close to its end of life. So always look for your oscillations here. Minimum of about 2, maximum about 5, maybe 6. But 5 is normally a good guide on it. So 2 to 5 oscillations indicate a good working coil, primary winding on that side. So that's a basic ignition signal on a primary waveform. So if we got up the secondary waveform on this car, we would see almost an identical waveform, slight differences to it, the main difference being up here, where I spike up to here. If it's a primary waveform, it will always be in volts. It can be anywhere from 200 to 400 volts or 450, whatever it is. If it was a secondary waveform that I was looking for here, this would be in kilovolts, so thousands of volts. Almost the exact same waveform, a couple of slight differences in it, because a secondary waveform is starting from nothing, so our start point would be 0, whereas our primary here is battery voltage, so our engine running voltage, so 12 or 14 volts. So we drop down to 0 for the dwell time here, as opposed to a secondary which starts at 0 and it slightly comes back up, but the same waveform will still be produced. We'll still see a spike, and we've talked a little bit about this in the theory. So available voltage and required voltage for spark on a secondary waveform. Remember, it should have a very high available voltage and its required voltage should be lower than it, which means that as the engine gets faster and faster, my required voltage is going to be more and more and more. I'm not going to come level with the available or exceed the available, because if I get up level with it and it's like that for a period of time, the likelihood is I will burn out that coil because the coil is operating at its max. So there should always be a difference on a secondary waveform between available voltage and required plug firing voltage. But that's a basic look, and if we really want to get in here and take a look at what's going on here, we can magnify that up again and see exactly what's going on here. So there is our sudden stop. Remember, this is our spark duration here, and then we drop the ball. So we oscillate out back onto our 14 volt running voltage. But it does not drop back down to 0, right? Remember, because I'm connected, if you take a look at the diagram again, I'm probed in here now. If that is open circuit, so I'll just do it like this. If that's open circuit now, voltage is pushing through here, pushing through the winding and coming out here. So what I'll see here is running voltage, let's say 14.2 volts. That's what I'll see there right now. Now once I close that circuit, or the ECU ignition control module closes that circuit and earths it, links it to earth. I am now on earth side of this is my load. If I'm on the earth side of it, it's suddenly going to drop down to zero, because zero is my equal. So I will always be like that, starting from a high, 14 volts. We earth the primary winding and dropping down to zero. So here's 14 volts, here's 0 volts. While it's connected to earth, it stays at zero. Then suddenly I break the earth. We spike back up. There's my spark duration. And we oscillate back to 14 volts. The period in here is my dwell time. In other words, how long current is flowing through that primary circuit. The peak up here to where I get to, remember on a primary winding, will be in voltage. So anywhere from 200 to 400 approximately volts is where that's going to peak up to. That's the giveaway sign, this one here, that this is a primary waveform I'm on. If it's anybody put one in front of you, because sometimes it's hard to differentiate between a primary and a secondary one. The difference is always going to be here, where that peaks up to. If that is a secondary waveform, it will be kilovolts we're looking at. And it will start from a zero here. It will start from a zero, not from battery voltage. Because if we look at our secondary winding here, it's not connected to anything. So we're just mutually inducing a voltage into it without it being connected to any sort of power source here for this particular system. Okay, so you'll see the notes on this in the book and take a look around at it. Make sure you can identify the waveforms and explain what's going on. The dwell time, the self-induction voltage peak on it, the spark duration time here, which is between that peak and that peak. Spark duration. And then these here, my oscillations. And what each of them means. So you should be able to look at a waveform and explain it out like that. Remember, if you're asked to pull up a waveform in an exam situation to look at this, or if it's a garage situation, you need to identify what type of coil I have. If I have a 3-wire coil like this, it will be an ignition primary waveform you're going to pull up. If it's a coil like this that has an amplifier on it and you're just probing in here, you're going to pull up a signal waveform, which will not be over 5 volts. It will be 5 volts and it will be a square wave you're seeing, an on-off signal for the base of the transistor, right? The control transistor. So knowing what to expect from each type of coil, waveform-wise, is where you should be. You should know what waveforms you can produce from it, knowing that this one will produce a primary waveform, this one will produce a signal waveform, and being able to check each, because you're going to come across these in garage situations where you need to be able to confirm the signals going to it, or it's good primary winding or secondary winding. And remember, for this one, if I'm checking it fully, right, make sure you have a positive here. Now, because there's a switch, earth switch in here, the only thing you can do here is make sure that wire between pin 1 and whatever pin number it is here is in good full condition, right? So continuity test on it, just to make sure, and a visual examination of all of the stuff for all systems, conditions of the connectors, conditions of the wires, making sure they're not cracked or broken, or you can't see them pushed anywhere, is part of examination of the ignition system. And it should be, often enough, people jump to look for something to change, whether it's module or coil, ECU, whatever it is, and disregard the wiring of it. And so some of the basic checks around cars are what they call eye tests or wiggle tests. Rather than holding the connector, you're wiggling the actual connector on to make sure it's in good solid condition. There's no breaks in the wires or the connector is only connected to the coil or the motor. So simple stuff first, and then get into skunk stuff as confirmation of signals or waveform diagrams. Okay, that's all for today, and we'll come back and have a look at coil-on plug the next day, the different types of coil-on plug and its progression through from where we started with 2-pin coil-on plug to 3-pin to 4-pin and what exactly they all mean. Okay, that's it. Thanks for that.